In the previous session, we have looked at the detailed steps to hand sketch ball plots for standard first and second order systems, with DC gain being 1. Okay, we didn't deal with any other DC gains. If your transfer function is not in a standard format, obviously you need to reformat it. Make sure you get them into the right format before you can calculate the corner frequencies for each of the first or second order transfer function. Now I'm going to move on and look at how we can use what we have done so far and add a little bit of extra work to produce ball plots for high order systems. Now that process will be built on the basis of what we have done so far. Okay, and if we are given a higher order transfer function, and that transfer function will consist of a number of first and second order subsystems. Okay, so what we will do is first of all we're going to break them into standard first and second order systems, like that one indicated in equation 1 for the first order and in equation number 2 for the second order. Okay, we'll get them into that kind of standard format. We deal with them individually as we dealt with the first order and second order system alone. Then we're going to add them all up to give us the ball plots of the high order. After we've done that, then we're going to deal with the DC gain of a high order system or first or second order systems, because we didn't deal with the DC gain before. Now we need to see how the DC gain can be included in the ball plots. Okay, so that is a process. Now to best do this, we're going to use some examples. Okay, I'm going to look at a couple of examples how we can break a high order into standard first order. Okay, and then how we deal with the DC gain. So in this case, in my first example, I have a transfer function GS equals to 25 divided by S plus 5 times S plus 0.5. Now that looks like a second order system, but it is also a combination of two first order systems. Where a second order system can be broken into two standard first order systems, that's where you have two real poles. The best is not to deal with, treat them as second order, treat them as two first order systems here. Okay, so I'm going to deal with this as there were two first order systems because they can be clearly separated. Okay, you only deal with the second order system in format, in sort of original format, if you can't separate them into two first orders. That means your damping is between 0 and 1. And in this case, you have complex poles and you can't separate them. Okay, so now what I have a 25 on the top. So I'm going to move 25 to the front. And then I have S plus 5 at the bottom. So I'm going to take that up away. That becomes 1 over S plus 5. And then I have second one, S plus 0.5. So I'm going to leave that in the last part. So that becomes 1 over S plus 0.5. Now, this is a first order system. This is a second first order system. Okay, and this is the coefficient or the gain. It's not necessarily DC gain yet, because this one, the two first order transfer functions are not yet in the standard first format. Okay, because for the format, to get to the right format, we need to make sure in the denominator we have 1 plus S times something, not S plus a number. Okay, so this number has to be 1. and this number has to be 1. Okay, so we need to do a little bit of reformatting. Now to reformat this, because I want that 5 to become 1, so I'm going to divide every term in that fraction by 5. To make this 0.5 to be 1, I'm going to divide every term here by 0.5. So divide this top by 5, divide the bottom by 5, divide second fraction every term by 0.5, divide the bottom by 0.5. Okay? Now, then I'm going to move this number to the front and that number to the front as well. So I get 25 times 1 over 5 times 1 over 0.5. What's left here is this becomes a 1 because I moved 1 over 5 away. At the bottom is s divided by 5. That becomes 0.2s. 5 divided by 5, that becomes a 1. So it's 1 plus 0.2s. Sorry, there's a mistake there. Plus 5 doesn't exist. Okay, note this term. For the second part, 1 over 0.5 is moved to the front. So if I divide s by 0.5, I get 2s. 0.5 divided by 0.5, I get 1. Okay, so combining all these values together, 25 times 1 over 5 times 1 over 0.5, that will give me 10. So these three numbers multiplied together will give me a 10. Multiplied by this transfer function, 1 over 1 plus 0.2s. Okay, so it's 1 plus 0.2s. This 5 doesn't exist, or should not be there. And then it's 1 over 1 plus 2s. Okay, so I have an overall DC gain of 10 because this is now in the standard first format. We know the DC gain of that is 1. DC gain of that is also 1. So overall DC gain is what you got left at the front. Okay, so we have 3 parts to deal with in this transfer function. Say the overall gain is A. This part, the first fraction, is a transfer function G1. The second part is a transfer function of G2. So the overall transfer function is divided into 3 parts. The overall DC gain, the first transfer function, the second subsystem. Okay, so for G1, which is 1 over 1 plus 0.2s, the coefficient of s is my time constant. Therefore, inverse of 0.2 is 5. 5 is my corner frequency. So for G1, I have omega C1 equals to 5. That's my corner frequency. For the second part, G2 equals to 1 over 1 plus 2s. Time constant is 2. Inverse of that is 0.2, 5. Okay, so therefore my second corner frequency is 0.5. That is the corner frequency for G2. And the DC gain is 10, but I need to convert that into decibels. So I'm going to do 20 log 10, which will give me 20 dB. So these are 3 values that I need before I start sketch my bow plots. Okay, so remember I have omega C1, that's corner frequency for G1. G1 is 1 over 1 plus 0.2s. Omega C2 equals to 0.5, which is for G2. And then I have an overall gain of 10 or overall gain of 20 dB. So I'm going to copy these 3 numbers down, and I'm going to put on top there and see how we're going to deal with that. Okay, I'm going to deal with G1 first. G1 is 1 over 1 plus 0.2s. Okay, so s is in the denominator, so we know the magnitude plot and phase plot will go down. Corner frequency is 5. Okay, so I need to sketch my plot, the axes. So I have frequency axis for that. I have magnitude axis. Okay, so I'm going to draw the magnitude first for this system before I move on to the phase plot, because I'm short of space. And I'm going to divide the frequency access by several divisions. I'm going to mark my two quarter frequencies here. So there's a 5 here, there's 0.5 here, and then I need to go at least one division below, that's 0.05, and I needed to go at least one division up from the highest quarter frequency, that's 50. Okay, so for omega C1, the S, both actually, G1 and G2, you have S terms in the denominator, so they both go down, but they have different quarter frequencies. When quarter frequency goes to 5, the bow plot starts from 0 dB, it stays on 0, it goes up, up, up until you get to 5. That's your quarter frequency. After that point, it's going to go down. Okay, so go down at the slope of minus 20 dB per division. So by the time you get to 10 times higher than the quarter frequency, that should be minus 20 dB. So I have this blue line for the 0 dB, I have this blue line for the decline slope. This is for G1, so this blue line here is the magnitude plot of G1. For G2, the magnitude plot, because the quarter frequency is 0.5, which is here. So the magnitude plot will start from 0 dB, which is marked as my red line. Okay, so it goes up all the way to the quarter frequency of 0.5. Now, beyond that frequency, it starts to go down. The gradient is the same. Okay, it's minus 20 dB per division. So by the time we get to the next division, this should get to minus 20 dB. That's the red line I have here. So that's G2. The blue line in G1 for G1, red line for G2. Now, the next thing you do is you're going to do G1 times G2. Now, because we use log scales, multiplication inside log becomes add if you expand it. So we can actually add the dBs together. Okay, so I'm starting, when you do adding, basically we want to add the blue line to the red line. Okay, when we do adding, you start from the very left of your graph. So you look at this here. I have 0 for the red, I have 0 for the blue. Therefore, G1 times G2 will be 0. When I move on towards my right, the first division I encounter is 0.05. So over here, blue is also red. Sorry, blue is also 0 dB. Red is also red dB. Therefore, 0 plus 0 is 0. Moving on to 0.5. Again, blue line is 0. Red line is 0, so that's another 0. Now, connecting all these together, that gives you the black dotted line. Okay. Move on. So up to here, we have 0 for the G1 times G2. Then I move to the next division. When frequency equal to 5, blue line, that's the G1, still is 0, but the red line for G2 is minus 20 dB. So 0 plus minus 20 dB, that will give you minus 20 dB. So you draw a dot there. Okay, and you connect from here, this 0 dB, and then connect to here. Next, dividing up, I have 50 radians per second. Now this time the blue line comes down to minus 20. But bear in mind the red line will go further down because red line dropped to minus 20 when the frequency is 5. By the time you get to another division, that should drop to minus 40. So it's minus 20 add to minus 40. That will give you minus 60. So at 50, G1 times G2 should be minus 60. And then you connect that line from there, just continue your black line, but with a different gradient coming down all the way to 60. That dotted or dashed black line is the magnetic plot of G1 times G2. That's partly why we want to use dBs. We want to use 20 log because multiplication becomes addition in logs. Okay, so black line is the plot, the magnetic plot for G1 times G2. The last thing we want to do, the final step, is to add the overall DC gain. The overall DC gain is 20 dB, or m equals to 10. So I need to add 20 dB to every frequency on the black line. So basically you are raising the black line by 20 dB. So 0 becomes 20, 0 becomes 20, 0 becomes 20. Minus 20 becomes 0, minus 60 becomes minus 40. So the green line is G1 times G2 and then times the DC gain. So the green line is actually the magnitude plot of the overall transfer function G. Okay, so do them in steps. First of all, separate the subsystems, make sure they are in the standard format, find the corner frequency for each subsystem, find the overall DC gain, work out the dB value of that gain. Okay? And then for each individual one, for each individual subsystem, deal with them as if they were single first or second order systems. Sketch the magnitude plot for G1, sketch the magnitude plot for G2, add them up, just go through different frequencies, find the values, and work out what you should have for G1 times G2 by adding the dB values together. Okay, connect all the points together, that will give you the magnitude plot of G1 times G2. And then final step is add the extra DC gain on top of what you end up. So I have the black dotted line for G1 times G2. Then because this is a positive 20 dB, the overall gain, then I need to add positive 20 dB to the black dotted line. If it was negative, then this graph would have to move down. That's for the magnetic plot. Now, for the phase plot, we're not worried about DC gain because DC gain is a constant. It doesn't carry any phase angles. Okay? Therefore, the overall gain does not affect the phase plot. All you need to do here is to draw the phase plot for first subsystem G1, draw the phase plot for the second subsystem G2, and then add them up at different frequencies. So over here, G1 has a quarter frequency of 5, so this is G1. So I'm going to draw that. I'll use a different color. G1, I use a red line here. Okay, the color scheme is slightly different. The G1 is, I'm going to change after the lecture so you get the right PowerPoint on Blackboard. Okay, I'm going to change the color afterwards. But for time being, this red line represents the phase plot of 5. So because the quarter frequency is 5, so the phase plot for G1 will start from 0 degrees up to the point that is 1 division below the quarter frequency. Okay, so 1 division below that 5 is 0.5. Then you're looking at 1 division above the quarter frequency, that's this division. And it's from there you should get a minus 90 degrees because the S is in the denominator, it's minus. And above 50, you get constant minus 90 degrees. For G2, that's now in the blue line. Okay, G2, the corner frequency 0.5. There. So 0 degrees start from very left, moving towards 1 division below the corner frequency. That's 0.05. And then you go to the 1 division above the corner frequency for G2. And that's here. And you start there with a minus 90 degrees. Above that, you're going to get minus 90 degrees. And then you connect up. So here, red line is for G1. Blue line is for G2. Okay? And then you're going to add them up to give you the phase plot of G1 times G2. Phase angle, when you do multiplication of transfer functions, the phase complex numbers, then you add the phase up. Okay? So start from very left. So red is 0, blue is 0, so that gives me 0. When I move up 1 division, red is 0, blue is 0, so also give me 0, so I'm going to connect them up in black dotted line. Moving 1 division up, at 0.5, red is 0, blue is minus 45, so I need to draw a little dot here and connect from 0 to minus 45. Moving another further division, red is minus 45, blue is 90, minus 90. So minus 45 minus 90, that gives me minus 135. So I need to go to where minus 135 is, make a dot there, connect that back to the end of my black line. 1 division, another division up, at 50, I get minus 90 and minus 90, that gives me minus 180. So I'm going to connect that up. Anything beyond 50 radians per second for the frequency, red remains constant on minus 90, blue remains constant on minus 90. So that will give me a constant 180 all the time. So that dashed black line is a phase plot of G1 times G2. It is also the phase plot of G, because the DC gain doesn't carry any phase angles. It doesn't affect the phase plot. It only affects the magnetic plot. Okay? So that's my first example. I'm going to run a second example as well. This time I have a second order system, but one S term is in the numerator and one S term is in the denominator. So I'm going to separate them into two, moving the top 5s plus 20 into 1. 1 over 5s plus 2 becomes second one. So I have 3 parts. That's some value times G1 times G2. But I need to make sure all the transfer functions for individual subsystems will be in the standard format like that. 1 over 1 plus s times a number. Okay? So I'm going to divide, for this, I'm going to divide every term by 20. For this, I'm going to divide everything by 2, because I want this 20 to be 1, I want that 2 to be 1. As the standard format, we have a 1 plus something. Okay? Now, when I divide everything by 20, I can move that 1 over 20 to the front. That's there. I can move that 1 over 2 to there. Remember, when you move 1 over 20 to the front, this is actually, you move from numerator, the denominator. So therefore, it should be marked as clear as denominator. So 1 over 20. Therefore, this term is actually be 20. Okay? 5s divided by 20, that gives me 0.25. Okay? And 20 divided by 20, that's plus 1. So it's a 1, it becomes a 1 plus something times s, which is good. This part, I already moved 1 over 2 to here. 5s divided by 2, that's give me 2.5s. 2 divided by 2, give me 1. Good, that's another subsystem in the standard format. Now I can combine the 3 terms in the front to give me the overall gain. So 0.01 times 20 times 1 over 2, that'll give me an overall gain of 0.1. This, I'll copy this down, and I'll copy this down. This will give me A, G1, and G2. So I'm going to see how we're going to deal with that. A is 0.1, G1 is 1 plus 0.25s, G2 is 1 over 1 plus 2.05s. So can work out the corner frequency for G1. G1 is going up now because S is in the numerator terms. Time constant is 0.25, therefore corner frequency is 4. For G2, time constant is 2.5, therefore corner frequency is 0.4. Overall gain is 0.1. 20 log 0.1 give me minus 20 dB. So these are 3 values that I need to sketch my Lucas diagram. Sorry, to sketch my boat diagrams. So I'm going to do this. I'm going to look at the first one. I have a corner frequency of 4, and I already sketched draw my axes here and made divisions. So I have 4 here, 0.4 here, 0.04, and I have 40 there. I have 20 dB, 40 dB, minus 20 dB, minus 40 dB. That's kind of stuff you have to do as a standard. Okay, so I'm going to look at G1 first. G1 has a corner frequency of 4, so my blue line indicates the magnetic plot for G1. So it's 0. It starts from 0 dB. You move along the frequency axis up to the corner frequency. Because the S terms for G1 is in the numerator, so it moves up. By the time you get to next division, this should be positive 20 dB. Okay, and then goes up continuously. That's blue line there is for G1. G2 is 0.4, the corner frequency. So the red line starts from 0 dB all the way up to the corner frequency of 0.4. And then because the S term is in the denominator, so it will go down. By the time you get to minus 20, by the time you get to the next division, it should be minus 20 dB. Okay, so this should be minus 20 dB here, and then that pattern continues. So blue line G1, red line for G2. To find the magnetic plot for G1 times G2, I need to add the 2 up, G1 to G2. Okay, so I'm going to start from left. Blue is 0, red is 0, so I have 0 here. This frequency, blue is 0, red is 0, so it's still 0. So I'm going to link them up with black dotted line. At 0.4, blue is 0, red is 0, so I'm going to link it up. At 4, blue is 0, red is minus 20, so I get minus 20. So I'll put a dot there, connect that back to this 0. Afterwards, if I go to the next division, G1 is positive 20. G2 will become negative 40 because at 4 it is minus 20. So at 40, because that continues to come down, it will be minus 40. Positive 20 plus minus 40, that will give me minus 20. So that's, I got 20 there, so I'm going to connect that back up. If you go further, you will get a constant minus 20 as well. So the black line, or black dashed line here, is the magnetic plot for G1 times G2. I'm going to, and then I have an extra gain. Now this time I need to make a change now, guys, because this doesn't make sense. This is minus 20 dB, okay? So I copy the wrong number here. So this one should be minus 20 dB. And now because everything should go down, this should be here. Now that's correct. Because it's a minus 20 dB, okay? Minus 20 dB means the black line, you have to add minus 20 dB to the black line. 0 add to minus 20, that's minus 20. 0 add to minus 20, that's minus 20. 0, minus 20. This is minus 20, add another minus 20, that's minus 40. So that line here is the magnetic plot for the overall transfer function, including the DC gain. Okay. Move on to the phase plot. Again, the overall gain, the DC gain doesn't affect the phase plot. The only thing I need to consider is the quarter frequency for the G1 and the quarter frequency for the G2. So for G1, I think I mix the color again. So this should be, this is G2, this is G1. The color scheme, it doesn't quite match. Okay, so the red one is actually for G1 because the quarter frequency is 4. Okay, and the S term, if we remember, if I just go back, S term is in the numerator. Okay, so S term is the numerator, the phase plot goes up. So 0 degrees all the way up to 1 division below the quarter frequency. Okay, that's for G1. Okay, so don't be misled by that color. Okay, this is G1. So quarter frequency G1 is 4. So we need to go from the 0 degrees, have to go all the way to 1 division below the quarter frequency. And then start from 1 division above the quarter frequency, that's 40. You should get positive 90 degrees and stay there. And then you connect them in the middle. Okay, that's G1 because S term is in the numerator. For G2, the quarter frequency is 0.4. The S term, if I just go back, S term is in the denominator. So therefore, it should go down. So I go, my phase angle start from 0 all the way to 1 division below the quarter frequency here. Okay, 0.4. The quarter frequency here. And this is 1 division below there, that's where 0 degrees stop. 1 division above the quarter frequency is 0.4. 1 division above is 4. So from 4, you get minus 90 degrees. And what's in between, you just draw a third line, connect them together. So red line for G1, blue line for G2. To find the phase plot for G1 times G2, which is also the phase plot of GS, you just add them up, frequency by frequency. So start from here, red is 0, blue is 0, so black is 0. There, red is 0, blue is 0, so black is 0. So I'm going to link everything up here. Next division, red is 0, blue is minus 45. So the black should be minus 45. Okay, so I'll put a dot there, and I'm going to connect them back. 1 division up, 4. This is positive 45. This is negative 90. So I get negative 45. So I put a negative 45, put a dot there, connect that back. A further division up, red is 90, blue is also 90, so I get 0 degrees. Anything above that, because this will stay as positive 90, this will stay as negative 90, so I get 0 degrees. So this black dashed line is the phase angle of GS. Okay? So basically, it really doesn't matter now. I'm only use example. My 2 examples only use 2 first order systems, but you could have got more, but don't be scared by the complexity. All you need to do is just treat them as individual first order systems. If they need to go up, they go up. If they need to go down, they go down. The key is to make sure you get the right quarter frequencies. Okay? That's where everything changes. For the magnetic plot, for the phase plot, you have to make sure you identify one division below the color frequency and you identify one division above the color frequency. That's where the lines intersect. Okay? So, I got 1, 2, 3 practical questions for you guys. You can actually use the examples to see how good you have to understood about the process of plotting both diagrams. Thank you.